guy who just wants to run for president. Can I be sexy? Sexy. Yeah, I definitely heard sex. Sexy.
Yell at me if someone else
Why? What was it? It was just like I'm talking about Starbucks. I don't even know where they're pretty much the same line. They wouldn't necessarily.
Yeah, guys,
Just different starting points. They're parallel.
okay, now I like that. So, do you guys think you can just sit in your chairs without any writing? Can you glance at these two sets of equations? Can you determine whether or not these lines are parallel? How can you say so?
Not just for one. Because the t values are the same. The t values are the same.
The coefficients of
That's
t.
exactly.
The values of the coefficients of t are the same, so I think these two lines have the same direction vector. They're definitely parallel. But now the question is, are they stronger than that? Is the relationship stronger? Are they coincident? Are they on top of each other?
No.
Because the things that you're adding to, the constants that you're adding to t are different.
But where do the constants come from that are in front? They come from...
The intercepts.
No, I think they come from a fixed point on a line, no matter where it is. And so I think for one equation, I'm talking too fast. I think for one line, I could have chosen infinitely many different starting points. So I think it's a possibility that these two lines are coincident. Unfortunately not, because I think we just have to worry about the initial point, not the entire equation, not the entire expression right inside the equations.
If they were coincident, wouldn't you be able to get starting point for one from the equation of the other?
Yeah, you would. I just think what you're saying is so strong. Let's make it weaker. If I could just find one point of intersection,
Yeah.
and they're parallel, they got to be the same line. So watch me cheat. I'm going to come in.
I like that.
You know what, you guys? I can't. I built this example in such a way that they were coincident, and I blew it. Can I change it? My apologies. I created an equation in my head, so they would become coincident, but I just checked and I blew it. So let me just change some numbers.
So you're saying they were just parallel?
Yes.
This first set was just parallel.
Jeepers, you guys, I gotta go slow. That's better. So, question. How can I determine?
Could you just set their x, y, and z components equally?
If I do, I get this.
Can you choose a value for t and find out what t is?
See, I like that. I'd probably come and do this, chimeras. I probably would ask myself, on this line over here, there is a point whose x-coordinate is 2, and I know for free what their y-coordinates are. And yeah, it may be the initial point, I just don't care, it's just one point on the line. So let me just find a t value in this line that gives me an x value 2. So I will take the initial point on the first line's x-coordinate and set it equal to the x-coordinate in terms of t on the second line, solve for t. And I think it's going to give me t being equal to 3.
And this is the 5.
What just happened?
This is to determine whether the lines are merely parallel or if they're stronger than that in their relationship coincident.
So what we did was we picked a value for x and solved for t.
Wouldn't
at
it be
that point.
wouldn't it be t is equal to -3?
No, I think that we neither 3 nor -3. I just got to be quiet today. Wouldn't t be actually a positive 1? Oh, I can't do it. What is that?
So if you add 1 to both sides,
Never
then
mind,
you
don't
get
listen to me. I don't know the arithmetic. Cheapers.
So we just picked
Half
a value
d.
for x.
Yes, and solve for t. I'm sorry if I'm butchering this. But I've just been pushing the arithmetic.
I
Dan,
still
I'm like
have-
this close to challenging this class.
Then every student would do that for all my classes. So you guys check this out. Since I think t equals -3 makes this x coordinate same as that one, let's just see if we plug -3 in for t here and here and get the same y and z coordinates over here. -3 in for t here gives me a y value of 3. Oh, look at that. That's it. Plugging -3 in for t here gives me a z value of,
-12 plus 1 is -4.
which is not the same thing as 5. And I told you I was going to force this example to be one where they're coincident. Okay, so I blew it again. But you do see the point. That's how you determine it. should I just go home?
So you substitute this one t value into all of the parameters for t in both equations, and if all three sets of coordinates for the two lines are the same, then they match.
Yes, and if I'm being too choppy with what I said, I like that. In other words, plugging this one t value in for t in each and every one of these, do you get the same corresponding point over here that you were initially looking at? Like, for example, 2, 3, and 5. In this example, it turns out it's not true.
So they're just parallel.
They're just parallel and not coincident. Not that that's what I intended.
But if all x, y, and z coordinates at that parameter t were equal, then the two lines would be on top of each other.
Yes, I think the value of the parameter t. Okay, so I
I'm
agree.
sorry, what's coincident again, like?
Coincident lines are just lines that are on top of each other.
So I said on top of each other, but not like.
They pass the exact
They're the
same.
same
They're the same
line.
line. In other words, if these are the same line, all what's really happening is that the entire real numbers stuck in for t span out the same line as the other equation, just at a different initial point.
If there was the same line, it would just be scalar multiples of each other then, right?
See, I disagree. I disagree completely because the direction would have to be the same no matter what.
Oh yeah, the direction has to be the same too.
And they could be multiples of each other, but they would have to be. And then I think for the x naught, y naught, z naught, there's going to be a shift, not a multiple of each other, in order for the lines to be coincident.
So, for a line to be coincident, do they not necessarily have to, wouldn't they only have to have 2 out of 3 parts be the same during any given value? The reason why I ask that is because, let's say, the x and the y values are the same, but the z values are different. So that just means it's going to be like this,
Yes.
and they are going to technically be on top of each other, but they're like that.
Okay.
He means passing through the entire same set of points.
Okay.
Yeah, when I said on top of each other, I meant slam. They're the same line. I
okay,
mean
why don't you
visually.
why don't you say they're the same line?
I thought I did.
Coincidence means like the same exact line.
Yes. Whenever you use that word geometry, I mean they're equivalent. They're the same shape.
It wouldn't for every value of t, they'd have the same coordinate.
Say
Or
that
x,
again.
y, z coordinate, for every value of t, then they'd have the same x, y, z.
No, I think they have the same x, y, z for different years.
Comparing that to the
If they're
other
close.
one, trying to find the t that they
But every point of line will be generated by 2 distinct t values in the parameter equation. You don't mind? Do this.
Yeah, so I was.
So do you guys agree that if I plug -3 in for t, here, here, and here, do you guys see how x, y, and z end up being nothing more than 2 and 3 and I hope -11?
Something like that.
Yeah, something like that. And so I think this t value gave me the point 2, 3, -11 on this line. But on this line, the t value that gives me that point 2, 3, -11 is not -3. It's actually going to be a 0 itself. Do you see what I'm saying?
Okay,
I'm
so
saying for a
different
given point on
times.
the coincident line, for one given point on that one line, it's going to be obtained by different t values potentially with the parametric equations. And notice this. Now that for my third example, I've got an example of coincident lines. Notice how this expression is not a multiple of this one, nor here and here, nor here and here. Do you see my point? Good point.
So are we doing 12.2 today, or are we doing something else?
12-3.
12.3? We're skipping 12.2?
Yeah, it's just going to be a piece of cake.
Okay.
So you guys, can we come back for a minute? Because some conversations in the math method were this morning. Oh, I know what chapter we're in. Jesus. So remember how I had you guys go home and take a peek at these equations?
Are we gonna need to have these memorized for the test, or are they gonna?
Of course. Actually, you're expected to already know.
You know, Aaron, you're great for moralizing the guy. Feeling terribly pessimistic.
Oh, no, it doesn't have an autofocus. Shoot.
It totally does. Remember, you had the same thing the other day.
Oh,
It
there
was
it
really
is.
crappy, but
That's fine.
Well, actually, in half the rooms, they've got an autofocus. doesn't have to burn together. And this one does not have that.
So janky, like.
So do you guys understand why the equations are what they are?
No.
I do. Let me talk about it. Because I went really fast in class, I did not specifically identify each and every one of these examples. I'm just gonna grab one. How about this? I sometimes refer to this as an elliptical hyperbola in one sheet. Ooh, I do. And I know standard form. It's just that I like to refer to this as an elliptical hyperbola for this reason. When I take a horizontal slice, a cut with a plane, parallel to this white border plane, no matter what c value I do that, the cross-sectional slice is going to be an ellipse. And with the equation, can you guys read this?
No.
If I plug 0 in for, or any constant for z, I think I get x squared over a squared plus y squared over b squared equals some constant. Isn't that just your standard math E form for the equation of an ellipse? However, if you take a peek at cross-sectional slices that are parallel to the z-axis, no matter what the x or y value is going to be, I think the cross-sectional slices are going to be collections of hyperbolas. And by the way, if I allow something like x or y to be 0, notice that's exactly what the trace is in those corresponding coordinate planes.
We would always get a hyperbola if we took cross-sectional, oh, you're saying, like, if the cross-sectional slice is kind of U-y like this, it's gonna always be a hyperbola.
Kind of U-y. Well, I just mean take a vertical plane and slice it anywhere through the surface.
But if you do that, aren't you just gonna get kind of like two, I don't know, little triangle-shaped doodads if you take it to the end of the hyperbola?
At the end of the hyperbola, what does that mean?
Okay, look at the picture. See it?
Yes.
Okay, so looking at the picture, if we were to cut the far end of the,
Like right there.
yeah, exactly, we wouldn't necessarily get a
Get very
hyperbola.
shallow looking.
But it goes on forever.
Yeah, this sheet goes on forever. It never stops. My
Okay,
apologies.
it's just,
And it's really hard for us to draw these surfaces by hand and show the reader that I really do continue on indefinitely both directions. But that's what's implied with this shape. And besides that, I can prove it to you mathematically speaking. If I slice like this, I can get that slice by, I don't know, letting y be 7. And if I plug 7 in for y, take that term to the side, I really do get my math key equation for hyperbola in terms of x and z.
right, that makes sense.
And if you let z equal 0, or you let z be constant, then you get a circle, you get a circular cross-section.
Well, in this case, since A and B are not necessarily the same, I get an ellipse instead of a circle. But you're right, if A and B are the same, that would be a circle. I understand. Now, I like to think of this one as an elliptical hyperbola of 2 sheets for this reason. Notice my picture, if I plug 0 in for z, there's no point on the surface. And if I plug 0 in for z here, you might not be able to see this, but I get negative x squared over a squared minus y squared over b squared equals positive 1.
And that's impossible.
And that's impossible to get with the combination of x and y values. That's why when I look at this equation, I immediately recognize it as a hyperbola of 2 sheets, not 1 sheet.
And if you don't like remember it like that, and you say it's like an upward goal and a downward goal, is that fine? The other one's like a nuclear
But when you
reactor.
use the word bold, it has no character to it.
It kind of looks like a bowl.
No, I understand that, but a bowl is it's just a bowl. Not every bowl is a hyperbole. Hyperbole has a very special quality that,
You could have a parabolic bowl where you could have a,
hyperbole has a very special quality that,
let me think.
yeah, I'll just.
Okay, I'm trying to remember. Okay, so this actually goes to a question that I had about this thing actually too. I see the cuts for the parabola and for the hyperbola in this conic section, right? But just to my kind of untrained layman's eye here, they look kind of like the same thing. So could you refresh my memory? on what exactly the difference is?
There's a big difference.
I'm
I think a parabola
Uh-huh,
has this quality. There's a very interesting point on the interior that's called the focal point.
uh-huh.
And if you draw a line past through that focal point in the vertex, kind of consider that a central line of symmetry. But if you plant your feet at that particular focal point and throw a projectile in any direction Durham please, you're going to hit the parabolic reflector and you're going to bounce off and run parallel to central line of symmetry.
Okay.
That's the reflective quality that parabola has. The honor students I have in Math 33 right now, they're actually answering a question which is this. If you got a shape that has this reflective quality, is it necessarily a parabola? And the answer ends up being yes, but you need differential equations to verify. Now, I think a hyperbola is so darn different. I get these two branches, and by the way, there's asymptotes in here as well. These two branches hug these two lines at extreme values of x and or y, whereas parabolas do not have equality. And the reflective quality that a hyperbola has is that if I stand on the outside of these branches, throw a projectile towards one of the focal points, I'm just not going to get there. I'll reflect off the hyperbolic reflector and run parallel, tend straight towards the other focal point.
Now, how's that useful?
You can ask.
Alright.
Y'all wait.
So like, let's say like shine a laser down, let's say that line's laser, and it bounces off that, then you're gonna bounce back.
Okay, you've got a good point. If these are solid, you can't pass through, I'll oscillate back and forth, tending towards that horizontal line, which is connecting the vertices of the hyperbola.
Oh, so you could like kind of trap something in there.
Oh, absolutely.
That's awesome. And then if you were to suddenly switch one of them off or something.
Like, so if like, let's say you like turn the laser off.
How about doing this, guys? Watch my colored pens.
It probably would absorb by the
Here's a
material.
parabola.
It probably eventually be absorbed by the material, but
Probably, yeah.
There is a vertex of the parabola.
here is something that would be really cool.
Here's a focal point of the parabola. Now create a small, how about a hyperbolic curve in red, where one of the foci for the hyperbola is actually at the location of the focal point for the parabola. But the other focal point for the red hyperbola is actually at the vertex of the parabola. And if I allow myself a little room in between those two curves, and have light come in, parallel to my central lines of symmetry, I'm going to hit the, oh shoot, in blue, that's a parabolic reflector. Tend straight towards the focal point of the parabola. I just don't get there because a piece of the hyperbolic reflector is in the way. But since I'm tending towards the focal point of the hyperbola, but it's also the focal point or one of the foci for the hyperbola, I'll hit the hyperbolic reflector and tend straight towards the other focal point for the hyperbola. It's just the engineer designing this system is certainly going to put a little slit where this vertex is of the blue parabola to locate the human eye's position. That's the way a basic telescope looks.
That is so cool.
So you can exploit these. You guys, I could spend 2 weeks not stop talking on applications of these conic sections. And you know what the shape of the ellipse is, correct? 2 foci. Throw a projectile in any direction. Hit the elliptical reflector and do one. Tend to the focal point.
Like that room in the Capitol building, where it like reflects sound kind of thing.
Yeah, actually, when John Quincy Adams, before he was president, when he was a member of the House, at the time they were meeting in the building that's since burned down. It's called Statuary Hall, where every state donated statues of 2 great men of their states. He was sitting in this huge room, and he was sitting at his desk, and the entire House was meeting, they're all talking. But he can hear whispers to somebody, and he knew who the person was, and knew that the person was at his desk over here. So upon further investigation, they came to realize that the architect, and I have no idea if this is intended, built the 2 ceilings as parabolic reflectors, not elliptical ones. And so the voices here at this table went in all directions, completely useless. Projected straight down the central line of symmetry, hit the other ceiling, which was a mirrored parabolic reflector, and tended straight towards what happened to be John Quincy Adams' desk. Nice non-technical eavesdropping device. But a lot of those whispering rooms are designed around the ellipse instead of the parabolas. Laser surgery. Same idea. Where a surgeon might not want to cut through human tissue. And here's a human body. There's something he wants to destroy. So he will put a portion of an elliptical reflector outside the human body. With the aid of a computer, he will make sure that the other focal point of the ellipse is located an object inside the human body he wants to destroy. And he will emit not light waves, but sound waves, sonic waves. So that the surgeon, he or she would be doing this with sound waves which are immediately completely useless. They're so weak. Pass through the human tissue, completely useless still. They're only useful when they get concentrated back at the other focal point. Where they're strong enough to maybe shatter that object into smaller pieces so the body can just flush those pieces down. Typically, kidney stones are taken care of like this. Wow. You know, there are 2 reasons, I think, 2 mathematical reasons why the Allies really wanted World War II. This is one of them.
Well,
Great.
another mathematical reason would be invading Russia.
The realized it.
There's that.
Never start a land
So
war,
who-
Jack.
A winter land.
So who fought the battle?
The British and
Yeah, the British, but also the,
the German Air Force.
yeah, it was a time of World War II where the Germans basically conquered everything in the European theater war. And the Americans weren't in the war yet. And the Germans were really successful because
Blitzkrieg combined.
yeah,
with the
they had a lot of nice toys. Because they got a lot of practice in the Spanish Civil War. And they really got advanced aircraft technology. But their technique was blitzkrieg, which means to go into countries at every level, ground, sea, air. They decided with England, they're not going to do it. Hitler decided or thought that he's going to have too many casualties. So he did something completely different from England. He embarked on the Battle of Britain, in which he was just trying to knock out the RAF, the Royal Air Force, with his Air Force called the Luftwaffe. And the Luftwaffe had a really nice plane. Their most destructive plane was
The Heinkel 111.
Dornier's, the fighter plane.
The 109.
And the British had nothing. And they knew they had nothing, just like the Americans. But one gentleman in England decided if he could just construct an airplane around an elliptical wing, he could potentially create an aircraft that had aerodynamic capabilities so that for the first time in history, at that period of time in history, somebody could fend off the German Luftwaffe. And he went to Parliament and they just laughed at him. Because to be able to create this airplane with this elliptical wing, it would cost 2.5 times the amount of money it takes for them to build their current fighter aircraft, which was completely useless against the Germans. But the English were getting scared enough, they finally built these planes, and they're called the
Spitfire.
Spitfire. They built just enough of them to fend off the Germans during the Battle of Britain. The Americans got hold of this. They loved this idea, and they built the...
No.
Well, the Mustang stole the engine, but we're Americans. We kind of bored out the cylinders a little more. It was
Was it the P-47 that was here?
the Thunderbolt. France.
So what's the electrical quality of the wings?
Now, I gotta confess, this is not an example of maybe the reflective quality of an ellipse, but he discovered that if he built a plane and wrapped around this elliptical wing, maybe shaved off a little bit of the front, the aerodynamic capabilities were so awesome that they could just actually defend themselves to the Germans. It was against the Messerschmitt, the German fighter. Well, actually, the Germans realized that us allies weren't very sophisticated. All our planes had, did you guys know what carburetors?
Yeah.
Oh, you do? Okay. I assume you all have to get fuel injection. But the carburetor is simply a device that mixes fuel with oxygen, puts in the cylinders so it can explode with cylinders. But the Germans had fuel injection. They realized with this really new fancy plane that if they were being chased by one, all they had to do is force really high G-forces. Because the Spitfire would come behind, having a carburetor, the gasoline wouldn't be able to get sucked into the engine. I'll stop. But anyway, because it's pertinent, you guys do need to understand what this is. I mean, this is a cone. And when I use the word cone in mathematics, I mean this. I'm talking about two intersecting lines. Where the angle bisector here is going to be the same as the angle bisector down here. And if you take these two lines and you bring them off the inport, wrap it into three-dimensional space, this is what a mathematical cone is. It's different than what you see in the ice cream shop because number one, it has two branches, and number two, it goes on definitely in both directions. And if I ask you guys to take a cross-sectional slice with a plane in this room, cross-sectional slice that's perpendicular to both the ink board and to the central line of symmetry. Oh, Caleb, do you have a green?
No, it's red right there.
Oh, here's a green. I think a cross-sectional slice perpendicular to the ink board, but also perpendicular to the central line of symmetry, you're going to get this shape, which is a circle. However, if I take a cross-sectional slice slightly slanted, then I think of blue, what I get is an ellipse. And if I take a slice parallel to one of the original lines I used to create the cone, I think I'm going to get a
Hyperbola? Or
parabola.
one of those two?
And I think if the plane is parallel to central line of symmetry, but not on it, I think I get two branches. Collectively speaking, we call those our hyperbolas.
So strictly parallel to the line that creates the cone, you get a parabola.
Yes.
And strictly parallel to the line of symmetry, you get a hyperbola.
Beautiful.
Now, what happens when you're somewhere between those two?
You know, you still get some of the shapes like hyperbolas, but I just stand there, it's easier to see if I just go parallel to central lines.
So the hyperbola is this way.
Yes, in a parabola slant. So when you look at this particular point, clearly there's my circle. Taking a slice, two-dimensional cross-sectional slice like slanted, there's mine. Ellipse. It's just that if you guys take a peek at this cone, notice how this particular slice right here is going parallel to central line symmetry, parallel to the central line symmetry. So I think collectively speaking, those are my two branches of mine. And finally, this slice right here looks like it's parallel to this line over here. And so I think that's where I get my The Greeks didn't really look at it this way. They understood some of the focal points, but the Greeks thought of a parabola, that's just an ellipse. That lost one of its focal points.
That one's like at such a shallow angle, it kind of looks like a vertical.
Yeah, it's kind of hard to see with this particular.
Yeah, that's what confused.
But that's really what it is.
So if you have a shorter, fatter cone, it would be more apparent.
I think so. You guys have heard all the stories behind the parabolas, aren't you?
Nope.
Who's the greatest mathematician ever?
Archimedes?
Yes.
Why? I guess.
Lots of reasons.
Archimedean death ray?
Yeah.
I saw that episode.
Look, if you take mathematics and make it into a death ray, that automatically makes you awesome. But then also the screw for getting water out of the
Archimedes
well.
screws that he gave the Egyptians.
The what?
Irrigating the Nile, he created an Archimedes screw. It's like a tube. I can't draw them. But it's a tube, it's empty, it's hollow. And if you put a pole